Hi guys, in this video I want to talk about Castelnuovo's inequality. Okay, so there's a classical theorem which talks about the genus of plane curves. So if you have a plane curve of degree d, so the lower index is the degree, then you can compute the genus of this curve in terms of the degrees, like so, if it's smooth. And if it's not smooth, then here you have these factors, and this is the multiplicity of a singularity at a point P. Okay, so I should say that this video is all going to be over an algebraically closed field of characteristic 0. Okay, so the natural question you can ask is, so what about, what's the formula for curves in higher, so curves of degree d in higher projective spaces? Okay, so this is a trick question. The answer is there is no formula. And I'm not exactly sure to what extent there is no formula. I'm not sure if it's just that we don't know the formula or that we can prove that one doesn't exist. Either way, what Castelnuovo's theorem does is it kind of it approximates what we want. Okay, so the theorem of Castelnuovo, or the Castelnuovo inequality, says the following. It says that, so suppose we have a map from C to C0, so in P of R, okay? And so this is a degree, so let's say that this is a degree D, D map. And then we have the following inequality on the genus. It says that there's some bound here. Okay, okay, so it's given by this formula, and here M is times okay, and I'm going to check real quick to see. I always flip these, so I want to see. So this is wrong. R minus 1. This is R M times R minus 1 is equal to D minus 1 plus or minus epsilon. Okay, so I think this is correct now. Let's see. So this is the floor, and when we multiply it, we almost get D minus 1. This is slightly smaller than the fraction, so this should be a plus epsilon here. Okay, so this is the theorem. Okay, so I'm going to fix some notation. Okay, so C is going to be a curve. D is going to be a divisor in C. Okay, and we're going to let this be the complete linear system, which can be identified with the projectivization of the global sections, or this is the divisors, the effective divisors, which are rationally equivalent to D. Okay, so here, this is the same thing as, well, this is the same thing as global sections of, with poles at worst D along this divisor. So this is global sections here. Okay, and so what we do is we take an F in here, and to get one of these guys, so this identification works by sending this to the following divisor. Okay, so this is this, and so these things only matter up to multiplication, which is why we're taking the projectivization here. Okay, so other notations. So RD is going to be the dimension of the linear series. Okay, and ID is the index of specialization, and this is H0 K minus D, like so. Okay, so yeah, this is just the index of speciality. You can see the video on Clifford's theorem. This explains this a little bit. Okay, so okay, so let me say something else. Okay, so I guess we should just start the proof again. So here's the setup. We have a map. Okay, this is the map induced by this divisor. Okay, so here this is an embedded curve, and let's fix the notation that so we can take a hyperplane section, and we could call this part D0, and then the pullback of a hyperplane section is going to be D. So again, this is a property of maps associated to divisors. Okay. Okay, so our strategy is to solve using to solve for G using Riemann-Roch. So let's write this out. So Riemann-Roch says that that we have the following equality. Okay, and so this equality, when we solve for G, gives us the following. It gives us that G is equal to LD. Okay, so we're going to take L big enough so that this goes away. Okay, so again, this is here, and so if the degree is large enough, this is going to have negative. So this difference will be negative, and this vanishes. Okay, so that being said, we can continue. This is LD minus R of LD. Okay, and our strategy will be to find to find an inequality here, but we'll subtract less. Okay, so we'll find a lower bound for our LD. Okay, so that's the idea. And to obtain this, we'll be showing that R of LD minus R of L minus 1D is less than or equal to some bound, essentially. Okay. So we have this linear series here, but we're going to look actually at a subseries. Okay, so here these are going to be so the point is, so let me just state what everything is, and then then we'll talk about what it all means. So these are hyperplane divisors So let's say, or hypersurface. So degree L hypersurface divisors. Okay, so they're the divisors that are obtained by intersecting C or C0 with a hypersurface of degree L. Okay, so and then we'll define beta of L to be equal to, okay, so if we can estimate the dimension here, so see that the dimension here is less than the dimension here. So let's take this will be the dimension of BL, okay? And so we would like to find, so the goal now, new goal, is to find a lower bound for beta L. Okay, so, okay, I'm going to introduce some another auxiliary, another thing. So beta L minus 1 is going to be related to, B of L minus 1 is going to be related to the following. B of L minus gamma. Okay, so here, these are going to be hypersurface divisors. So these are going to be the hypersurface divisors, linearly equivalent to L, the effective ones, which vanish along the pullback of a hyperplane section gamma. Okay, and so our claim, one of our claims is that so if let's say gamma is the pullback of, let's say, so this is a generic hyperplane. Let's say gamma 0 intersects C0, and so this is a divisor on C0. Okay, so the idea is that I of C0 minus, so I of, so which one's the bigger one? I of gamma 0, so gamma 0 is contained, let's see, I should say this, maybe H0, this is gamma 0. Okay, so gamma 0 is contained in C, so it's ideal, right? So the ideals are reversed. Okay, so this thing here of L, so the dimension of this is equal to the dimension of BL minus gamma. Okay, so this is the idea. So let me explain a little bit about these things. Okay, so some observations. Okay, I don't know how I'll do them. I guess I'll do the first one. Let's do it like here. Okay, the first one will be here. Okay, so here I want to talk about this inequality. So not all elements of this linear series are divisors coming from the embedding. Or not the embedding, divisors. From, let's say, hypersurface sections. Hypersurface in PR. Okay, so not all elements of this are the same. Okay, so the potential difference is that there could exist some divisor in this system here, which is not the pullback, right? There could exist some dl prime, which is not equal to the pullback of some section like this. Okay, it may be equivalent to one, but it might not be the effective one. Okay, so I think this is the issue here. Okay, so the second point is that, so I want to talk about this shift here. Okay, and I want to talk about this correspondence with sorry, this is supposed to be BL minus 1. So I want to talk about this correspondence here between BL minus 1 and BL with this gamma shifted. Okay, so first, so what we can do is if you take one of these and then shift by a gamma, so we take a guy in BL and we shift by gamma, right? Then what we'll end up getting is something that has degree L minus 1 but may not be effective. Okay, so note in a priori effective. Okay, so yeah, so they're going to give you things but all are related, are linearly equivalent to LD. Okay, that's because this is just related to D. It's just another hyperplane section. Okay, the second thing that I want to say is that the map. I want to say that it's so that that BL minus 1 is a subset of BL minus gamma. Okay, so that this is actually injective. So this is strictly, this is bigger. Okay, so for all of these guys, there exists a guy in here. Okay, so let me say I'm still doing the observations. To see search activity, okay, so what we do is you take an element of EL minus 1, okay, so we'll take some divisor here, okay, and what you can do is you can add, okay, DL minus 1 plus gamma, okay, so this thing here is an effective divisor. Okay, and it's linearly equivalent, it's equivalent to LD. Okay, because this is linearly equivalent to L minus 1D, and this is linearly equivalent to D. So they're both hyperplane sections, or pullbacks of hyperplane sections. Okay, so this means that this thing is an element of LD. Okay, and so the map that we described, so this implies, so hence this shows the backwards process of taking the negative thing has all elements of EL minus 1. Okay? Okay, so now the third observation. So I'm going to give you a description. This is going to be a description of this claim. So this claim here. So description, proof, whatever. So first, notice that gamma 0 is a subset of C0. So this tells us that I of gamma 0 is contained in I of C0, which tells us that I of gamma 0 of L contains I of C0 of L. Okay, so here, these are the degree, this parameterizes degree L hypersurfaces containing C0, so containing the curve. And so similarly, this is the degree L hypersurfaces containing that hyperplane. Okay, so using this, the description, this dimension, so of the, so this is the big one, this is the small one, okay? So this is equal to the number of independent degree L hypersurface divisors divisors of C0 vanishing on gamma 0, right? And yeah, so okay, so you have to. What I wanted to say is you kind of have to think about this. This is a little confusing for me. I mean, like I had to think about this for a little bit. So something to think about. So think about here. So okay, so here it's pretty much the same thing as this, except for you're just replacing these. These are all arbitrary hypersurface divisors here. So these are like arbitrary. So when we distribute the L, this thing here is arbitrary hypersurfaces of degree L, right? And here we've restricted to the case of hypersurfaces which contain that hyperplane. Okay, so this is this, and this thinking about this will shows the claim. Okay, so now it remains to compute. Okay, so beta L minus beta L minus 1. Okay, so again, beta L is the dimension of BL. Okay, so this is greater than or equal to, so beta L is, so this is the dimension of hypersurfaces in PN or PR of degree L vanishing at on I of C0. So these are the hypersurface sections. Okay, and then here we're going to use that claim. So this is I of gamma 0 modulo I of C0 of degree L. Okay, and so we use the exact sequences here to split this up. Nope. L, let's say minus I gamma 0 of L minus dimension of I of C0 of L here. Okay, these cancel, and we see that this is just the dimension here of degree L hypersurfaces, so the number of independent hypersurfaces of degree L, and then this is the number of hypersurfaces of degree L that contain gamma. Okay, so this is really like so the number of dependent hypersurface sections of gamma 0, or hypersurface divisors. Okay. Okay, so here's a lemma, which if I am going to show it, I'm going to omit the proof, but maybe I'll say something about it when I do, or if I do, the geometric version of Riemann-Roch for curves in characteristic 0. Okay, so let's state the lower bound is that so S P of R mod I gamma 0, this thing. So this is bigger than the following. Okay, and the proof of this comes from considering spans of points. Okay, so you look at certain particular spans of points. Okay, so now putting these two together, right, we get beta of L minus 1 is greater than or equal to the minimum of dLr minus 1 plus this. Okay, so this is what we want to do, and we want to telescope this out. So now the goal is to telescope. First, I want to make an observation here. So a little computation. Let's just do it over here. Okay. So when these two things are equal, okay, we find that d minus 1 over r minus 1 is equal to L. Okay, so the breaking point where one's smaller, where d becomes bigger than this, is this magic number m, which is d minus 1 over r minus 1. Let's see if we did this right. D minus 1 over r minus 1. Okay, so that seems correct. Okay, so now I'm going to telescope this out. And I'm going to sum from, so notice at 0, this is a linear series of degree 0, so we can put that in. Okay, so, and then we're just going to sum. So at m, so this is the sum from L is equal to 1 up to m of L r minus 1 plus 1. Okay, so this is equal to r minus 1 plus this sum of L, and then plus, and then this is just m terms. So this is r minus 1, and then we have m times m minus 1 over 2 plus m. Okay, we can simplify this a little bit, but let's go back to the Riemann-Roch computation at the beginning. So let me show you again what that looked like. So here, okay, and so now we have this lower bound, which is that sum. Okay, so we have this lower bound. Okay, so G is equal to LD minus RLD. So this is less than or equal to LD, and then we have our lower bound. So the lower bound is, and L is equal to M in this case. Okay, so we have, this is R minus 1, M minus 1 divided by 2, plus M. Okay, so this is M, okay, so we have, so this is MD minus R minus 1, M times M minus 1 divided by 2 plus M. Okay, so maybe I didn't really do anything here, huh? I just replaced the L with the M. Here we can factor a little bit. So let's factor. So this is let's see what we have here. So this is M times R minus 1, M minus 1 divided by 2 plus M, or plus 1. Okay, so let's call this star. And I'm going to simplify this a little bit down here. So here, so I'm going to finish out the proof of Castelnuovo's theorem. Here we go. So now we have the following inequality given from what we just deduced. Okay, in the description what we had before. And we can see, okay, so we can sum this up. We pull out the R minus 1. This is R minus 1, M times M plus 1 divided by 2. And then here we just get M. Remember here that M is equal to D minus 1 over R minus 1. So we have that that R minus 1 times M is equal to D minus 1 minus epsilon. Okay, so we'll call this star. Okay, and then remember the computation at the beginning. We had this is equal to MD minus R of MD, okay, which is less than or equal to, okay, now we're just going to plug in everything, MD, and now we have this lower bound, so this is R minus 1 M times M plus 1 divided by 2 plus M. Okay, so this is ugly, but this is essentially the Castelnuovo bound already. So this is what we have. And so this is equal to M times D minus 1 minus R minus 1 M times M plus 1 divided by 2. Okay, so all I did is I combined these two here. Okay, and then let me just say that this is a fact. So you can do a computation, right? I'm just not going to repeat it right now. It's just ugly. It's ugly any way you do it. There's kind of like two choices you can do. You can solve for either R or D, but you can't completely eliminate R and D together. So we end up getting that this is M times, so let me already say this. This is already pi of RD, okay? But I'm just going to write down Castelnuovo's bound here. So the form that I presented it in the beginning, this is M plus epsilon. And then we use, this uses this formula here, okay? There's a fun fact, so that there's also an asymptotic for this that you can check, which is not difficult to do. This is, that the limit of this is asymptotic to, so the large D limit is this. Okay, so all I mean by this symbol is that the limit as d goes to infinity, the ratio of these two things approaches 1. Okay.